We say that a function is one-to-one if every single x value in the domain happens to be mapped to only one y value in the range. Mathematically, to check that a function is one-to-one, we're going to do the following. We're going to take two values that are inside of the range. We're going to call those values f at a and f at b, and we're going to set them equal to each other. And we're going to trace them back and see if this equality implies that our two original x values are equal. If this is the case, then we're going to be able to conclude that our function f is one-to-one. So to get a better idea of what this implication means, let's take a look at a couple examples. Let's show that the following linear function is one-to-one. F of x is equal to 2x minus 3. What we're going to do first is assume that we have two y values that are equal. That is, we assume that f at a is equal to f at b, where a and b are numbers inside of the domain of our function. We can evaluate the left-hand side. F at a is going to be equal to 2a minus 3. So here I'm just going to use the rule of our function and substitute a anywhere that I see the value of x. We can do the same thing on the right-hand side. F at b, using our rule, is going to be 2b minus 3. From here, let's add 3 to both sides. That's going to give us 2a is equal to 2b. And then we could divide both sides by 2. And we see that a is equal to b. So what exactly have we shown here? Well, we've shown that if we start with two y values that are equal, our two corresponding x values inside the domain must also be equal to each other. This means that if we pick two different x values inside of the domain, they're going to get sent to two different y values inside of the range. This means that our function f of x must be one-to-one. Next, let's show that the function f of x equals 2 minus 3x all over x plus 1 is also a one-to-one function. We're going to begin like we did on the other slide with f of a equals to f of b. That is, we take two y values and set them equal to each other, and we're going to try to work backwards to see if the two x values also have to be equal in this case. Next, let's substitute the value of a into f of x. So we're going to get 2 minus 3a all over a plus 1. We're going to set this equal to 2 minus 3b all over b plus 1. Now I'd like to note here that the value of a is not allowed to be equal to negative 1. We can't substitute the value of negative 1 into our original function f, so minus 1 is not inside the domain. This means that we're free to multiply both sides of our equation by a plus 1. By doing this, we've cancelled off the denominator on the left-hand side, and that leaves us with 2 minus 3a. And over on the right-hand side, we're going to get 2 minus 3b times a plus 1, all divided by b plus 1. Now again, we want to note here that b is not equal to minus 1. So this allows us to multiply both sides by b plus 1. And once again, this is going to get rid of our denominator over on the right-hand side. And we're going to be left with the following expression. b plus 1 times 2 minus 3a is equal to 2 minus 3b times a plus 1. So we're going to have to go ahead and distribute. Working through the left-hand side, we're going to get 2b minus 3ab plus 2 minus 3a. Expanding out the right-hand side, we're going to get 2a plus 2 minus 3ab minus 3b. Now in red, let's start balancing out either side of the equation. I'm going to subtract 2 from both sides, and let's also add 3ab to both sides as well. So on the left-hand side, we'll be left with 2b minus 3a is equal to 2a minus 3b. Next up, I'm going to subtract 2a from both sides. On the left-hand side, this is going to leave us with 2b minus 5a. And the right-hand side, we're going to have negative 3b. And then finally, to finish everything up, let's collect our b's. So subtract 2b from both sides. And this will give us negative 5a is equal to negative 5b. Dividing through by negative 5 is going to give us a is equal to b. And this is what we need in order to make our conclusion about one-to-oneness. Since a is equal to b, and we started with f at a equals f at b, our function f of x must be one-to-one. So we might be interested in why we care about one-to-oneness of functions. Well, the real importance here is that if a function f happens to be one-to-one, we're going to be able to find a special function called the inverse of f. So taking a look at the drawing that I have down here, if I have two sets, a and b, and I define a function on a that is one-to-one, that is every unique value inside the domain gets mapped to only one value inside the range. So f here is what we call a one-to-one function. If f does happen to be one-to-one, then we can create a new function we call f inverse that does the opposite kind of mapping. It takes the elements that we have inside of the range and sends them back like this. So in red here, we could call this f inverse. It's the function that undoes what f has done. Let's go ahead and formally define what we mean by an inverse function. If we start with a function f, and we compose with a function g, and we end up getting the function x. And this is true in the reverse direction, that is if we take g and compose with f, and we also get the function x, then we call f and g inverse functions, or inverses of each other. Often what we do is we write g as f inverse of x. To give you an idea of how to show that functions are inverses using the definition, let's take a look at the two functions f of x equals 7x minus 4, and g of x is equal to 1 over 7x plus 4 over 7. What we have to do is we have to show two compositions are equal to the function x. First, let's start with f composed with g. Remember, this means everywhere we see x inside of the function f, we're going to substitute in the function g of x. So what we want is we want 7 times g of x minus 4, or 7 times 1 over 7x plus 4 over 7 minus 4. And if we distribute the 7 through, we're going to get x plus 4, and then we still have that minus 4. Our 4's are going to cancel, and we're going to be left with just x. So that side looks good. Next we move on to g composed with f. This means everywhere we see x in the function g, we're going to substitute in f of x. So we're going to get 1 over 7 times f of x plus 4 over 7. Or we get 1 over 7 times 7x minus 4 plus 4 over 7. I'm going to distribute the 1 over 7 through. We get 1 over 7 times 7. That's going to give us just x. 1 over 7 times negative 4 is going to give us negative 4 over 7. And then we have that 4 over 7, that positive 4 over 7 to deal with. That positive 4 over 7 will cancel with the negative 4 over 7, and we're going to be left with just x. So what we have is we have that both composed functions give us what we call the identity function x. So these two functions must be inverses of each other by the definition. The last thing that we might want to be able to do, given a function f, is to actually calculate the inverse function. To calculate the inverse, we follow the following 3 steps. First, we're going to replace f of x with y if it's necessary. Step 2 is to interchange x and y. That means every x we're going to replace with y, and every y we see we're going to replace with x. After we've done this, the last and final step is to solve for y. After you've isolated y, the resulting equation is going to be the equation for your inverse function, f inverse. In our last example, we're going to try to find the inverse of the function f of x equals x minus 2 all over x plus 2. Now over here, I'm just reminding you about the domain of f of x. We're not allowed to substitute the value in negative 2, so we're just going to keep that in the back of our minds as we work through this problem. Our first step is to replace f of x with y. So I'm just going to write down y equals x minus 2 over x plus 2. And from here, we're going to move into step 2, which is to switch all of the x's and the y's. So everywhere I see y, I'm going to replace that with x. And everywhere I see x, I'm going to replace that with y. From here, we're going to try to solve for y. So I'm going to multiply both sides by y plus 2. This multiplication is going to allow us to cancel off the denominator over on the right-hand side, and we're going to be left with y minus 2. On the left-hand side, we're going to get y plus 2 times x. Continuing on from here, we want to distribute the x through our brackets on the left-hand side. This is going to give us yx plus 2x is equal to y minus 2. And then remember that our goal here is to solve for y. So what I'm going to do is I'm going to subtract y from both sides. And I'm also going to subtract 2x from both sides. I'm going to do this so that I have yx minus y on the left-hand side, that is all of the y terms on the left-hand side, and I have negative 2x minus 2 over on the right. So anything that doesn't contain y, I want on the right-hand side. I'm going to then factor out y from these two expressions. So this is common factor. We're going to be left over with x minus 1. And then I want to divide both sides by x minus 1. So here, we can only make this division as long as x is not equal to the value of 1. So we should restrict that here, or state that restriction. Now that we've solved for y, we have our inverse function. Our inverse function f inverse of x is equal to negative 2x minus 2 divided by x minus 1. Alright, my little epsilons, stay positive.